we'll be discussing the stress-strain analysis. Stress is a quantity expressing internal forces that neighboring particles exert on each other, while strain is the measure of deformation of the material. The ratio of stress and strain provide the modulus of elasticity for the material, which provides insight into how much material can take before permanent deformation. The analysis of stress and strain in materials is imperative to all branches of engineering, from infrastructure such as dams, bridges, and tunnels, to aircraft parts and structural materials. The stress and strain analysis is an important part of the manufacturing process.
This is the stress and strain diagram. It shows how the material behaves in a certain way. In the elastic region, if pressure is applied before it reaches its proportional limit, the material will return to its original shape. Once the material reaches yielding stress, or past the proportional limit, the material will begin permanent deforming. This is commonly called plastic deformation. At this point, the object will continue to elongate with a constant load. When the object reaches strain hardening, the object will get stronger through plastic deformation. Once the object reaches necking, its cross-sectional area will start decreasing, which is caused by a large amount of strains over a localized part of the material. After this point, the material will enter fracture stress, which will result in the object to break.
Machine tools use very hard materials that have a very high yield point, which is why they're able to remove material without deforming themselves. Consequently, are very brittle, and any erupted cut can leave in a broken insert. This goes to show that material selection and testing is very important. Here we have a SOLIDWORKS simulation of a part we plan to test in real life. Knowing what we know now, we can use shear, stress, and strain to our advantage, cutting this bar to length. Here we're applying large amounts of shear stress to remove material from this part. We're going to machine this to 0.9 inches long and leaving the diameter as it was from the factory at 0.625 inches. At the hydraulic press, we can apply large amounts of normal force, but we won't need it because copper has a very low yield point compared to other materials. We can reach plastic deformation very fast. Here we can see the final diameter and lengths and the buckling of the part, just as it was in the SOLIDWORKS simulation. All we have to do is take final measurements of the length and diameter. Here we have 0.0831 inches for the final length. And the final diameter is 0.662 inches. Knowing these dimensions, we can calculate the latitudinal strain, and that's equal to the final diameter minus the initial diameter all over the initial diameter, and that's equal to 0.00592. We can also calculate the longitudinal strain, which is equal to the final length minus the initial length all over the initial length, and that's equal to negative 0.0767. We can also calculate Poisson's ratio, which is equal to negative the latitudinal strain divided by the longitudinal strain, and that's equal to 0.722. We can find the normal internal force by working backwards, finding stress first. We know stress is equal to the modulus of elasticity times the longitudinal strain. The modulus elasticity for copper found online was 125,000 megapascals times the longitudinal strain that we converted to metric, which is negative 0.0767, and that's equal to negative 9,525.0 0.52 megapascals. So now that we know the stress, we can calculate the normal internal force. We know the area. We know that the internal normal force is equal to the stress times the area. And that's equal to 7.7 Newton meters squared.